Well, welcome. Here we are again. This will be Lecture 29, Chemistry 106. I hope you're doing your reading. You guys have actually done a terrific job. I'm really happy with what's happened in this class. But let's move right into the lecture. I don't want to waste any time here. The solubility in a solution, the solubility of a substance in a solution is not the same as the solubility product constant, or KSP. This is just a fancy name for an equilibrium constant. KSP is just like any other equilibrium constant. We have Ka, we have Kb, we have Kw, we have Kc, K sub p. We have all these Ks where the subscript here just helps us understand what we're talking about. How on earth they came up with solubility product to indicate a poorly soluble salt in water, I have no idea. But when we see KSP, we know we're talking about a dissociation of an ionic substance. It's a salt, sparingly soluble, and we expect these values here to be really small. Typically 10 to the minus 10, 10 to the minus 15, 10 to the minus 20, something like that. So really small numbers. But in any case, the solubility is different from the solubility product constant. This is just an equilibrium constant again. The solubility of a material is the amount of it, the quantity of it, that will dissolve to form a saturated solution. So we can describe the solubility of a substance in water simply by the concentration that we find at equilibrium. How much is dissolved, that's the solubility. So again, we can describe the solubility quantitatively by just talking about the concentration of whatever species we're dealing with at equilibrium. So once again, the solubility product constant, this thing's an equilibrium constant. We kind of beat that to death. I've got a couple of problems here that I think are very, very relevant. And I think that they illustrate a number of important concepts regarding buffers and KSP values. But as you can probably see, all of this equilibrium stuff ties together, whether we're talking about acids or bases, or we're talking about KSP values for sparingly soluble salts. At the end of the day, it's all just equilibrium, and it kind of manifests itself in slightly different ways, but the principles certainly spill over into the different areas. So let's learn this and make sure that we understand this. Because again, I think this is an important problem. So we've got some cobalt 2 hydroxide. The 2 refers to the oxidation state or the charge on the cobalt. So this would be cobalt 2 plus, and then we've got 2 hydroxides. But in any case, we add it to a magical buffer that holds the pH of the solution at 12.5. Okay, so I have this ability. Again, a buffer doesn't really do that. A buffer doesn't really hold the pH of a solution constant, but we're going to assume we have this magical buffer. So when you come back and you say, but wait, how did you know that the pH stayed constant? And the answer is it's magic. I have this ability to hold the pH of the solution constant, but we're going to see what happens as a result. So in any case, I add some of this salt into a solution. pH is 12.5. And again, it's held there, and the question is, what's the concentration of the cobalt 2 plus at equilibrium? And so let's do what we've done before. Let's write some kind of a dissociation for our sparingly soluble salt. So here's the cobalt 2. I guess I could say it's a solid, and it is. It's going to dissociate into ions, so I get CO2 plus 2 OH minus. And what we don't know yet is we don't know what the concentration of the hydroxide is. But here's what I'm going to do. But I can figure it out. If I know the pH of the solution, let's see. So of course we know that pH is the negative log of the hydrogen ion concentration. And so this means that H plus is equal to 10 to the minus pH. So I just took the negative of both sides and then used the fact that the inverse function of log is 10 to some power. And so again, I can take this number right here, 12.5, stick this in here, and this gives me the hydrogen ion concentration in the solution. And we don't expect it to be very high. In fact, we expect it to be really small. So I've got, let's see, 10 to the minus 12.5. Just put it into my calculator, and so I have a hydrogen ion concentration of 3.16 times 10 to the minus 13. Certainly a very, very small number. And now I'm going to kind of just skip a step, but I'm going to tell you what I'm doing. And so we all know that if we have the H plus concentration, we can find the OH minus concentration because this concentration times this concentration is Kw. So if I just take Kw, which is 1 times 10 to the minus 14, and divide by this, I should have an OH minus concentration. So let's see, I take 10 to the minus 14, and I get an OH minus concentration of 3.16 times 10 to the minus 2. Okay, so I think that's all good. And this looks like it's going to work. If I take this times this should equal 10 to the minus 14. This times this looks like that's going to be about 10. And this is 10 to the minus 15. 10 times 10 to the minus 15 is 10 to the minus 14. So it seems like the numbers are making sense. And that's a good idea, is to kind of check your numbers for reasonableness as you go along. Does it make sense? Yeah, 10 to the minus 13, 10 to the minus 2. I see what's going on here. In any case, let's now write down what our initial conditions are. We're not sure if we're going to do a BCA table or an ICE table, but let's certainly go ahead and put in the initial concentration. So we say that we put some of this in water, and my initial concentration here of the hydroxide ion is determined by the buffer is 3.16 times 10 to the minus 2. And I look at this situation and I have none of this cobalt, and the question is, am I close to equilibrium or not? And the answer is probably, because let's see, the KSP for this material, it has a really small value, so I expect the cobalt concentration to be really small, and this just isn't going to change, and it's not going to change because I have this magical buffer. And again, we can contemplate what the effect of this buffer would be on this equilibrium, even though there isn't really magic out there. Okay, so so what's going to happen? Let's see. Let's run an ICE table. We recognize that we're close to equilibrium. I'm going to let some dissolve, and I'm going to get a plus X here. And normally what we would do is we would write plus X here, but because of my magical buffer, I'm just going to write plus 0. So I'm not cheating here. I explained that I have a buffer that can absolutely keep the pH constant. That means the OH minus concentration stays constant. So because of this little magical buffer right here, no change occurs here, even though we're not at equilibrium. This equilibrium expression, this has to be enforced, so we have to have some dissociation of this, but the buffer is going to adjust to keep this concentration constant. So at equilibrium, I have a concentration here of 3.16 times 10 to the minus 2. I have a cobalt ion concentration of 2, and I have some left. So, and I know I have some left because that's what I was told. Some of this is present. It's left there down at the bottom of the beaker at equilibrium. So, to solve this problem, I say KSP is equal to, and now I just have X times the concentration of the hydroxide ion squared, 3.16, times 10 to the minus 2 squared. And so I'll just go ahead and solve for X. So I'll take the KSP value, which is this, I'll divide it by this squared, and I have X, which is the cobalt ion concentration, is equal to, let's see, so let's take 1.3 times 10 to the minus 15, and let's divide that by 3.16 times 10 to the minus 2. I'll square that, I'll divide, and I'm going to get 1.3 times 10 to the minus 12 molar. That's a pretty low concentration, but that's what it predicts to be, and the answer is 1.3 times 10 to the minus 12. So we did the problem right. And there are certainly points here where we could have written out more. We could have, written out the algebra here and here. But I think we've explained how we got to it and how we solved this problem. Again, How come we didn't have a 2x here? Because the buffer is able to magically adjust and just hold this pH constant so no change takes place, even though some of the cobalt hydroxide is dissolving. Whatever amount of cobalt hydroxide dissolves, the buffer is able to adjust for that and hold the pH constant, hold this concentration constant. But besides, this is such a small value that, we would have neglected it anyway, and this is minuscule compared to this and really unmeasurable. But okay, so this is how we solve the problem, and this is an interesting and important problem because it illustrates so many of the concepts that we're dealing with. But I'd now like to throw you a little bit of a curveball here. It's going to be the same problem, except we have a buffer that is now holding the pH at 2.5. So instead of being very high, we're at a rather low pH. And so let's see, we've got, let's see, KSP for cobalt hydroxide. It's the same value, obviously. So now we're adding the substance to a magical buffer, still magical, but this time we're holding the pH of the solution at 2.5, a rather low value. What's the equilibrium concentration of cobalt 2+? Okay, so same game as before. Let's see, I've got cobalt. Let's see, cobalt hydroxide in equilibrium with cobalt 2+. And of course, we should all be able to look at something like this and see how it dissociates into ions based on what we've learned in this class and Chem 105. And so let's see, we have some of this initially. We don't know the initial concentration here, but we could figure that out. Again, let's see, we know that the concentration of the hydrogen ion is equal to 10 to the minus pH, and we're given the pH. Let's see, the hydrogen ion concentration here is equal to, let's see, I've got 2.5, and I take 10 to that power, and I get 3.16 times 10 to the minus 3 molar. But now what I've got to do is I've got to figure out the OH minus concentration. Same game as we played on the previous slide. H plus concentration times OH minus concentration is Kw. So I'll take Kw and divide it by this. And now I have a very small number. I have an OH minus concentration that's 3.16 times 10 to the minus 12. And of course I can look at these numbers, and the math is basically the same as what I had before. It is the same as what I had before. So H plus times OH minus is equal to 10 to the minus 14. It's all working and it's all good. Okay, but the OH minus concentration is 3.16 times 10 to the minus 12. Let's invoke Le Chatelier's principle here. On the previous slide we did a problem where the concentration of the hydroxide ion was high. What is that going to do to this equilibrium? And the answer is it's going to push it to the left. Now we have a situation where the hydroxide ion concentration is extremely low. That's going to pull the equilibrium to the right. We would expect that. We would expect that the solubility of the cobalt-2 would increase a great deal. Another way of looking at this, and it's perfectly right, and so we can solve the problem this way, but another way of looking at it is to say I've got a fairly high concentration of H+. And so every time a cobalt hydroxide dissolves and I make hydroxide, it's going to react with this H+. And so if I keep removing this, so a little bit of this dissociates, I remove the hydroxide, well then more has to dissociate by Le Chatelier's principle. So no matter how we look at it, it looks like this material is going to be really soluble under acidic conditions, but not under basic conditions. If I have basic conditions, I have a high concentration here of hydroxide. This equilibrium I'm not pulling this material. The equilibrium is not going to the right here. The dissociation is not going to the right. Now I have an extremely low concentration, and now it is. Okay. I think I said that right. So we've got none of this to begin with. We have this magical buffer. It holds this pH constant here, so extremely low hydroxide concentration. I'm going to run an ice table here because this isn't going to change and this isn't going to change. There's just one thing here. So I'm going to let some dissociate. So I'll just say I've still got some and I've still got some at equilibrium. I'm going to get plus X here. I'm going to get plus 0 here. Why plus 0 again? Because this buffer just holds the pH constant. Somehow the buffer can adjust to whatever the cobalt hydroxide is doing. So I have X here, and I have 3.16 times 10 to the minus 12. And so I have KSP, pretty much just as we did before, is equal to X times 3.16 times 10 to the minus 12 squared. And now X is equal to, so again, I'll just take, I'll get this number from here, divide by this squared. So I have 1.3 times 10 to the minus 15, and I'm dividing by 3.16 times 10 to the minus 12, that really small number. I'm going to square that, divide, and I get, okay, I think I did something wrong. 1.3 times 10 to the minus 15, I put it in my calculator wrong. 3.16 times 10 to the minus 12, that's good. And now I get, just give me 1 second, I apologize. 1.3 times 10 to the minus 15. Yeah, I get 1.3 times 10 to the 8th. Okay, and that's molar, and this is the concentration of cobalt. Now you might say this looks a little high, and in fact it looks extremely high, and in fact it's really not even possible. We can't have a concentration this high. I mean, the matter is just too dense. If you think about water itself, what is the concentration of water in water? How many moles per liter? How many moles are there in a liter of water? And the answer is about 55. And so 10 to the 8th is absolutely ridiculous here. So what's going on? Let's see if we did it right. Yeah, okay, so we did it right. And then the question is, can this be right? What does this mean? And the answer is it means something. And what it means is that this material right here is freely soluble under these conditions. And so when I have an acidic set of conditions, and I have something that's basic right here that's producing hydroxide, once again, and we've said this before, but I think it deserves repeating, as soon as any hydroxide goes into solution, I've got a fair amount of H plus here. In fact, I've got this continuous supply of H plus that can just react with the OH minus, and they will react. And so that will draw this material into solution. It pulls the equilibrium to the right again and again and again. It causes more and more dissociation by Le Chatelier's principle, because once again, every time some OH minus is produced, it's removed, and so more dissolves. And so what we see is that we have this material as freely soluble under low pH conditions, whereas if we have very high pH conditions, then the dissociation is not favored. This material doesn't dissociate, because then this concentration is so high. Okay, so let's go to this next problem right here, and I think that all of these problems again are very, very relevant to what we're talking about. Suppose we have a saturated solution of lead iodide in water. Okay, you add a little of nitric acid to it. Will this addition of nitric acid change the solubility of lead iodide in this solution? And again, Mr. Gilbert, Skyline High School, when you don't know what to do, do something. So I've got this sparingly soluble salt. I have lead 2+ that's formed. I have 2 I minuses here. And let's go ahead and just write down the dissociations for all of the species that we're dealing with here. And we want to do this for 2 reasons. And the first one is what we had talked about before. We want to see what effect do these different species have on solution pH. And let's see, we know that, well, H plus obviously is going to drop the solution pH. Nitrate has no effect. I minus has no effect. We know that. Lead, we would expect also lower the pH. So certainly we're going to have a low pH solution. This would act as a weak acid. This is, of course, a strong acid. But what we see is we have an acidic solution, and that's important. But the other question that we need to ask ourselves here is, do these ions interact with each other? And so this is a second question, a second idea that's kind of being thrown out in this lecture, is not only should we have the ability to look at individual ions and see how they affect solution pH, we need to look at the interactions between the ions. How are they interacting with each other? Well, I don't expect a positive to interact with a positive or a negative with a negative. They repel each other. But what about lead and nitrate? Do they interact? Is this in some way going to change the lead concentration, which would then change the equilibrium concentrations and cause either more or less of the lead iodide to dissolve? I think and we know the answer is no. Nitrate salts are freely soluble in water, so the nitrate is not going to change the lead concentration. Well, how about this interaction here? Is H plus going to perturb in any way the concentration of I minus in this solution? And the answer again is no, it's not, because this is HI is a strong acid, which means that we have complete dissociation, and so H plus has no affinity for I minus in solution. So the answer is putting HNO3 into a solution that has some lead iodide in it. We've come to equilibrium here, so this equilibrium is operative. I add in some nitric acid. I don't change this equilibrium because I'm not affecting the concentrations of these species at all, so the answer is no. Okay, so once again, when we think about a solution and we have multiple ions in it, we need to be asking ourselves the questions, how do these ions affect the solution pH, and can some of these ions interact with each other? Let's go on to the next slide because I think that this is going to illustrate the point pretty well. Now we have some magnesium fluoride. It's not very soluble, low KSP value as we'd expect, but we have some magnesium fluoride that's in water. So again, most of it is sitting at the bottom of the beaker. We have just a little bit of it where we have Mg2 plus 2F minus here. And we play the same game. We've got this equilibrium that's operative, so we dropped this in water, we waited some time, the solution came to equilibrium. I've got these ions in solution, small amounts of these, I've got this at the bottom of the beaker just sitting there. But now I add some nitric acid to this solution, HNO3, and let's see, I get H plus NO3 minus. And so the question again is, what's happening to the solution pH? Well, I would expect that putting F minus into solution that would certainly raise the pH. This is a weak base. It's going to interact with water. We've seen that lots of times. But the question here is, how does this material right here change the solubility of the magnesium fluoride? So do the presence of these ions right here in any way change these concentrations and thereby change the solubility of the magnesium fluoride, the amount of it that will dissolve in solution? So once again, we look at these two ions and we say magnesium 2 plus and nitrate. Well, no, there's no interaction here. Nitrate salts are soluble in water, so these don't interact at all. But what about these two right here? And we certainly see that this is a weak base and a strong acid. And when we have a weak base and a strong acid together, they pretty much just react. So this is going back to what we saw with the cobalt hydroxide, that when we were putting hydroxide in solution, when we had a basic species, if we had an acid there, it would react with it, and then we would change the solubility of the material. So again, if I add nitric acid into this solution, I significantly change the solubility here of this material, because the F minus loves, the weak base loves to react with the strong acid, and once I form HF here, then I've reduced this concentration, and by Le Chatelier's principle, more of this dissociates, so the solubility gets changed a lot. In fact, magnesium fluoride is going to be very soluble in an acidic solution. I can get this to dissolve basically by putting it in acid, so I do change the solubility significantly here. Okay, so let's see. Here's a little example. Here's a salt. It's dissociating into ions. We have a KSP value for it right here. Of course, we remember that at any time for any set of conditions, Q is equal to the concentrations of A plus and B minus. We know, of course, that if Q is KSP, we're at equilibrium. And another way of saying this is to say that the solution is saturated. No more the concentrations of A plus and B minus are not going to increase once Q is equal to KSP. We've saturated the solution with this material. Again, no more of it dissociates, because then we wouldn't be at equilibrium anymore. And of course, we remember that if Q is less than KSP, again, we have Q here, this number is smaller than KSP, then to get to equilibrium, Q has to get bigger. That means these concentrations have to get bigger, and that means that this right here has to dissolve. So more of it dissolves. And if we have a situation where Q is greater than KSP, then we're going to have a precipitate form. And this is the first time that we've seen this idea, is that because these two ions, when they react, form a solid, if I have a solution where this concentration and this concentration, according to this rule right here, if these concentrations, when I multiply them together, are bigger than KSP, so now Q is greater than KSP, this reaction goes to the left, as we've seen before, and when it goes to the left, a precipitate forms. Okay, so let's see. This is another one of those problems that's just a little bit challenging, and it's one of these problems that, again, is something that most students have to think about a little bit. But let's see what we're given. We're talking about something called selective precipitation. And the idea with selective precipitation is that if I'm careful and if I do things right, I could add in an ion that would cause one ion to, so I've got two ions in solution. I could add in another ion that might cause one of them to precipitate while it leaves the other one in solution. And that could be kind of valuable because it's a way of separating two ions from each other. So let's see, what do we have? We have barium fluoride has a KSP value of this, and we have lead fluoride that has a KSP value of this. And what we're seeing is that the lead fluoride is less soluble than the barium fluoride. So by about a factor of 100, again, this material is less soluble. The KSP value is smaller. Now let's consider a solution that's 0.1 molar in both barium nitrate and lead nitrate. Okay, again, nitrate salts are soluble in water, so this really means that I have a 0.1 molar solution with Ba2+, and at the same time, in my same solution, I have 0.1 molar of Pb2+. The question is, what's the highest concentration of F- of fluoride that could exist in this solution without either ion precipitating? Well, to solve problems like this, again, we have to go back to this issue of which is the most soluble species. It's this, because it has the larger KSP value. This is the less soluble species. And all we have to do is concern ourselves here with the least soluble species. What I'm going to do is I'm going to say, the lead is more sensitive to fluoride to fluoride in solution than is the barium. Based on these numbers, I could put more fluoride in the barium solution. If I had two separate solutions and I were adding fluoride, I could put more barium, I could put more fluoride in the barium solution without seeing a precipitation than I could in the lead solution, because the lead fluoride is less soluble. It's less tolerant of putting fluoride in. And so what I'm going to do is, and I think I should actually prove this to you, and so I think we'll do this, is let's just consider this equilibrium right here. And so let's see, we've got PbF2, and I've got Pb2 plus 2F minus, and I'm going to say this is my concentration of 0.1 molar, and I'm going to say that I'm at equilibrium. And the truth is, I'm at the edge of equilibrium. Maybe none of this is formed, or maybe just a molecule or two, or the tiniest bit of this is formed, but I'm going to say I'm at equilibrium right here, and I'm just going to say if I had this concentration of lead, what would be the equilibrium concentration of F minus here? Okay, so let's do this really quick. If I'm at equilibrium, this is an easy calculation. KSP is equal to 0.1, sorry about the sig figs, times x squared. And so we have x is equal to, then we've got KSP over 0.1, and I'll take the square root of that. So let's see, the KSP value for the lead fluoride is 3.6 times 10 to the minus 8. I divide by 0.1, I take the square root, and I get now a fluoride ion concentration of 6 times 10 to the minus 4. That should be an equal sign, times 10 to the minus 4 molar. And so we are, again, right on the edge here. This number works for an equilibrium calculation. If I put this number in here and I square it and multiply by this, I will get this concentration, I will get this KSP value. So again, I'm right at equilibrium right here. I've put as much fluoride in as the solution could handle. If this concentration got any bigger at all, then my Q value would be bigger than KSP and a precipitate would form. So I submit to you that this is the answer to the problem, that this is the highest concentration of fluoride that can exist in this solution without either ion precipitating. And now you're going to say, but what about this right here? And what I'm saying is this is this is more soluble than this. So if I can put this much fluoride into solution and this won't precipitate, certainly this one won't precipitate either. Let's do the calculation. Let's kind of prove it. So we've got barium fluoride, and let's see, we've got Ba2 plus 2F minus, and my barium concentration here was 0.1. And now let's just take this fluoride ion concentration, 6 times 10 to the minus 4. And we don't know whether we're at equilibrium or not, so let's calculate a Q value here. So I'm going to take this value times this value squared, and let me see, I'll just do that. Also, I'm going to square this times 0.1, and I get 3.6 times 10 to the minus 8. And in fact, you look at this and you say, oh, what you really did is you just put in these are really just the equilibrium concentrations for this. But now my Q value here for this barium fluoride, oh nuts, okay, my Q value here for this barium fluoride is this right here, which is certainly less than KSP for barium fluoride. And so what this tells me is that if anything, the reaction wants to go the other way to get to equilibrium. So no precipitate will form here. And so I really have answered the question. This is the highest concentration of the fluoride that can exist in solution without causing either of these species to precipitate out. And yeah, that is the answer right here. Oh, good question right here. Let me get out of this and jump back in. So let's do this question now. What is the highest concentration of fluoride ion that could exist in this solution that would precipitate one ion but not the other? And so again, we can sort of see the game that we're playing. Which one of these is going to precipitate first as I slowly add in fluoride? Well, this one, because it's less soluble. We saw that with the math. We can see this because of the size of this number compared to this number. But now, what's the highest concentration of fluoride I could have that would drop out one ion, obviously this one because it's less soluble, and not this one right here. Okay, so let's see, how do we do this? Well, all we really need to do then is focus on this one because, okay, so let's just solve this. Okay, barium Ba2 plus 2F minus. I have 0.1 molar concentration of barium initially. The question is, what's the highest concentration of fluoride I could have in this solution? Well, that's going to be an amount X, and I'm at equilibrium here. And so you might ask yourself, how on earth do you just say you're at equilibrium? And I say, well, this is really a question. If I were at equilibrium, what's the highest concentration of fluoride I could have in this solution? And so I'm going to say KSP is equal to 0.1 times X squared. And now X is equal to, let's see, KSP for barium fluoride is 1.7 times 10 to the minus 6. And I'm going to divide that by 0.1, and I'm going to take the square root, and I get 4.12 times 10 to the minus 3 molar. And again, this is now the very edge of solubility here. If I put any more than this into this solution, so this is equal to the fluoride ion concentration. If I put any more fluoride in solution than this right here, then this would give me a Q value that's greater than KSP, and a precipitate would form. So I'm at the highest level of fluoride I could have in this solution that should precipitate this and won't precipitate this. Well, let's prove it to ourselves. Will this concentration of fluoride cause a precipitate to form here? And so let's quickly do that. So I've got lead fluoride in equilibrium with Pb2 plus 2F minus. I've got 0.1 molar here. The concentration of the fluoride is going to be this right here. Let's calculate a Q value. Here we don't know whether we're at equilibrium or not, so I get 0.1 times, again, this value right here, squared. Okay, so 4.12 times 10 to the minus 3. I'll square that. I'll multiply it by 0.1. And this gives me a Q value of 1.7 times 10 to the minus 6. And I say, will it precipitate form? And the answer is yes, this material will precipitate out because this right here is greater than this. So Q is greater than KSP. I'll just write it's greater than KSP. And of course, this is the KSP right here for the lead fluoride. Therefore, a precipitate will occur here. And so what we're seeing here is by carefully choosing the concentration of the fluoride ion, I could put in fluoride that would not cause the barium to precipitate, or at least here I'd be just on that very edge of causing a precipitate to occur, while I would cause the lead fluoride to precipitate out. Okay. Okay, so I guess, yeah, we did get the correct answer right here. What was the highest concentration of F minus that would exist in solution that would precipitate one ion but not the other? And that's the answer right here. And then we just did this extra calculation. Okay, so let's talk briefly about titrations in polyprotic acids. And what I want to focus on in this slide is just the shape of this titration curve right here. And just recognize that if you have a polyprotic acid, and here we have a diprotic acid, we're starting here with carbonate, CO3 2-. It picks up a proton, and then it picks up a second proton. And most of you probably know that H2CO3, or carbonic acid, will actually break up into carbon dioxide and water. But in any case, what we have for this titration curve is two equivalence points. And so this is what you should be able to recognize, is that if I start with this base, carbonate, CO3 2-, I'm adding in the strong acid right here. I have one equivalence point. That's where now I've put on the first proton, and then I've got a second equivalence point where I've put on the second proton. So this is the type of curve that we get. So it kind of comes in steps. And it would be the same thing if I had a base that had two protons I could put on it. I'm sorry, if I had an acid that I could deprotonate twice, and I would again, or three times, I would have a kind of a staircase shape to it. Next problem, let's see, KSP value for magnesium hydroxide is this. An excess of magnesium hydroxide is put at the bottom of a beaker of 1.5 molar sodium hydroxide. What's the concentration of Mg2 plus at equilibrium? So good problem, and certainly one that we should know how to solve. So I've got magnesium hydroxide here. It has a small KSP value, so it's not very soluble in water. I get Mg2 plus 2OH minus. This is the dissociation. We should all be able to write that down. We have an excess of this material that we put into a beaker of water. The concentration of the hydroxide is 1.5 molar. And once again, there's this important question. Some of you say, well, there's a 2 here, so why don't you multiply this by 2? And the answer is, once again, these concentrations right here are the actual solution concentrations. That's what's given in the table. The concentration of the hydroxide ion from the sodium hydroxide is 1.5 molar. So that goes here. That's the actual solution concentration. This right here is a rule that tells me how this dissociates. Every time one of these dissociates, I get one of these and two of these. Okay, so let's say that we have none of this to begin with. Let's run an ICE table. Why would we run an ICE table? Well, we look at these concentrations and we say, well, the magnesium ion concentration is about 0 here. We certainly don't expect very much of this, especially because we've got a ton of hydroxide. So if anything, this is pushing the solubility towards the left. By Le Chatelier's principle, if I have a ton of this, then I'm pushing the equilibrium in the other direction. So let's see, my change is I get some dissolves, and so let's see, I'm going to have some dissolves. I still have to have a little bit of the magnesium at equilibrium, so I get plus X plus 2X right here. And now we're in a situation where we're, again, trying to figure out how to get to equilibrium. We don't have a magic buffer that holds the pH constant, and so I've got to put in the 2x right here. So this is different from the problem that we looked at earlier. I've still got some I've still got excess magnesium hydroxide. When I'm done, I've got a bunch at the bottom of my beaker. I've got an amount x. I've got 1.5 plus 2x here, and I will neglect this. I am betting that with this huge concentration right here of hydroxide ion, the solubility of the magnesium too is going to be so low that x should be tiny. So I have KSP for magnesium hydroxide is equal to x times 1.5 quantity squared, and x, which is the concentration of magnesium. Let's see, we should be able to solve that. So let me throw the numbers in my calculator. I've got KSP, which is 1.8 times 10 to the minus 11, and I'm going to take 1.5 and square it and divide, and I get 8 times 10 to the minus 12. So 8 times 10 to the minus 12 molar as my concentration of the magnesium, and that's really quite low. And so again, we can see the effect of another ion on the solubility of the magnesium hydroxide. It's smaller than it would have been otherwise. I would encourage you to solve the problem whereby you just put magnesium hydroxide into water, and then you look at the concentration of magnesium just in water without that extra hydroxide. And what you'll find is that the concentration of the magnesium too is much higher. So the answer was 8 times 10 to the minus 12. So I guess this concludes the lecture. Just a few minutes shorter than before. Well, actually, I will create a little bit more content than for this. So let me finish this, and then I'll find some more problems to work on.